Good morning. I would like to thank the organizers for invitation to give this talk, where I'll be talking about polymeric icephobic coatings, some of the recent developments mainly in academic research laboratories. We are also working on the same, problem. However, I will not be talking about, our work yet because it's not finished. This is a brief summary of my talk. Of course, as we all know, especially in the northern regions, ice and snow accumulation on various outdoor structures have many problems. So we will discuss them as a simple introduction. Then I'll talk about, design strategies for icephobic coatings, because people have used many different materials, many different approaches to, solve this problem. We will discuss them in detail. And then, we will draw some conclusions and maybe discuss some future work. Again, we are lucky in Turkey because we don't have too much snow, at least not in Istanbul. But, in the northern part of the world, especially, North America, Russia, and, Canada, ice and snow accumulation has very serious consequences. For example, disruption of services. Even last year, they went through this in Texas. They didn't provide electricity. And then this may cause substantial economic losses. And sometimes it's even possible to have loss of life. So this is a serious problem which needs to be, solved with a simple approach. So that's what I'm gonna discuss, during this presentation. Now here, we have some pictures. So the systems affected by ice snow accumulation, of course, rooftops. For example, here in picture C, there is a, cathedral somewhere in Russia. As you can see, everything is frozen. Of course, power transmission lines, they may freeze and, this may cause, just like in Texas last year, serious problems. Of course, planes, cars, marine vessels, especially airplanes, they are de-iced, like as you can see in picture A. And various other things, military installations, telecommunication systems, refrigerators, we all use it, and ice accumulation causes problem also with air conditioners. However, here, most of the people who worked, whom I will be discussing their work in this, talk, try to develop coatings for wind turbines, because wind turbines, as you can see, in picture B, if they are, onshore in the mountains and things like that, where there is really, good flow of air and wind, they can get frozen in the winter time. So therefore, and now it's getting so popular that, they are building these, wind turbines almost all over the world. So it's necessary to develop efficient coating systems that would prevent icing, because if there is ice, usually you have to shut down your system, and then it also, of course, creates energy shortages and loss of profits and the other things. And in fact, here, I was really amazed when I saw this picture. So this, ship, it looks like it's an old picture, and it's all frozen, and people are trying to break the ice, mechanically. As you can see, this is amazing. I've never seen anything like this, but obviously it's happening. So basically, if they had an ice coating, it would be much easier to remove the ice and, prevent all the problems. So, I hope you have a vision, you have a, good idea now what this problem is. And another problem is, people are trying to understand how ice forms and sticks to the surfaces, because there are, ice formation is a complex process, and it can happen, under very different conditions. For example, we may have frost in the morning, or it may come in form of snow at different temperatures. For example, freezing rain, which is, something I have seen in the United States. It rains, but it freezes as soon as it hits the surface. If you are driving your car, then suddenly your windshield is totally frozen and you can't see anything. Then there is super cold water, which is way below freezing point of water, which can, just freeze immediately. There is fog icing, in-cloud icing. This is especially true, for airplanes and things like that. So again, people are, in addition to trying to develop new materials, people are also trying to understand the mechanism of, water freezing or ice forming on the surfaces so that they can find, solutions for this process. Now, there are several parameters that may affect, ice formation and ice adhesion to surfaces. Of course, one of them is temperature. I mean, it may be just around 0 degrees or just below 0 degrees where, snow and ice may form, or it may be done at, minus 20 degrees. And again, their mechanisms are different, their adhesion problems are different. So, you have to understand and solve this problem. Of course, humidity is another parameter. Contact time, for example, it's whether within seconds or minutes or other things. For example, if a wind turbine is turning, then the contact time may be, shorter. Of course, wind speed may be important. And then the chemical structure of the surface, as I'll show you, may be important. It's surface energy and, roughness and the other things. So all these things will affect ice formation and adhesion to surfaces. So basically, we need to understand all these things in order to be able to solve the problem. Now, current strategies for combating icing. Again, active heating. For example, on the airplanes, when you're flying up on, 10,000 meter high, they have to heat the surface of the cabin. Or in many parts of the world, even for wind turbines, they have heating systems. Of course, which uses lots of energy, but it, prevents at least the shutdown. Or as we all know, if we flew in wintertime, there are lots of chemical de-icing fluids, starting with, ethylene glycol. So they de-ice, airplanes. You can do the same thing, for wind turbines or all other things. But of course, these are really environmentally toxic. So they create lots and lots of problems. Another one is mechanical removal, as we have seen, in the previous picture where people were trying to de-ice a huge, vessel. So with this, of course, the preferred solution will be a durable and easy to apply polymeric icephobic coating. So basically, you will just apply it as a paint, and if it dries out as a paint, if it is durable, that's what you want. So it's very, very, at least sounds simple. Now, the desired properties of a high performance icephobic coating would be very low ice adhesion strength. Normally this number was less than 100 kilopascals. However, to have really, really high performance, coating, it should be less than 10 kilopascals. And in fact, I'll give you lots of numbers on lots of different systems. And as you will see, none of them has really achieved this number yet. They came very close, but as far as, I can see, it's a magic number. We have done some experiments in the lab. We can get, maybe lower than this time to time. But again, to commercialize it will take lots of effort. And it should be simple to apply, just like a paint with a brush or, with a roller or with a spray, can, whatever. And it should just dry out. Preferably, it shouldn't be curable. It shouldn't need any curing, because curing means high temperature, long times. And then another problem is, it should be easy to repair just in case if there's a damage. Of course, it should be durable and it should be environmentally friendly. Now, what are the benefits? Of course, it will improve safety. It will reduce maintenance cost if it's effective. Of course, reduce energy consumption. And it is, if done properly, will be environmentally friendly. And then, if you can develop a good material, it would be simple to apply and convenient to use. So basically, these are some of the benefits. I mean, of course, we can add other things to this. And that's when we want to solve this problem, we have to keep all these things in mind. And this just shows, as a scientist, of course, when you do something, you want to share it with the rest of the world, either as a paper or as a patent. And this shows a number of publications from 2010 to last year or so, a number of publications on anti-icing coatings on the top, on the left-hand side. So as you can see, it's increasing dramatically. On the right-hand side is the number of citations. I mean, this is important for scientists, but of course, not that much for industrialists. And then, so this is for all anti-icing coatings, about 200 papers. Maybe in this year, it may be 250, maybe more. But one of the approaches, as we will discuss, is super hydrophobic coatings that may act as anti-icing coatings. And in fact, almost half of the papers are related to the super hydrophobic anti-icing coatings. I mean, my experience, because I did work on super hydrophobic coatings, we can convert any polymer surface to a super hydrophobic surface, but I do not believe this is the solution. Solution is somewhere else. However, people still work quite a bit on this, and I'll talk about this, in the coming slides. Now, of course, we have to design experiments to measure the strength of ice, its adhesion strength to the surface. And here also, there are several different approaches. I mean, one that's very widely used is shown in the next slide. I mean, here what you do, you have your sample. You have your samples. And here on the test substrate. And then you have these, cuvettes, usually polystyrene cuvettes. You fill them up with water to almost a half, and then put your sample holder on top of this and turn it around, and then freeze it at -10 degrees in this case. I mean, this is the paper. You can find actual procedure in this paper, which is published by MIT and US Air Force and a few other people. And then you freeze this, and then you measure the force by using a transducer. So this is, again, this may or may not reflect the actual situation. Why? Because, again, here we are starting with, liquid water and freezing it on the surface. However, if it is ice, and if you are, looking at the turbine surface, this really doesn't mimic that system. But this is the conventional, method that most people use. We also use the same thing in our labs. And in this, experiment, you push this, ice cube, and then you measure the force. Usually you get something like this. And this peak will give you removal force in kilopascals. And then the area will give you the removal energy. So this is typical. Of course, it may not be like this. It may be in different forms. So you can understand the mechanism of failure also. This is a work done by, Ken Wynn, a good friend of mine. I'll give some more data for him. And now let's talk about, what type of materials are used for, icephobic coatings. Again, there's lots of them. As you can see, I mean, people have used siloxanes, fluoropolymers, biomimetic coatings, liquid filled surfaces, which we will talk about. Of course, surface texturing, like, this super hydrophobic surfaces. They even use metals. They modified metallic surfaces by using fluoropolymers and things like that. So as you can see, lots of things. This is a nice, review paper that you may find all these things, if you are interested in. And people also compared, ice adhesion to different material categories. For example, if you use a hydrophilic surface, adhesion is usually pretty good because, I mean, ice is very hydrophilic. If you use hydrophobic surface, just simple hydrophobic, I mean, you may go down to almost, 10 kilopascals. So these are like, silicones or fluoropolymers. And here is super hydrophobic. Again, as you can see, you may go down to 20, 25 kilopascals. And of course, Eisenberg and her group at Harvard, they do this lubricant or slip surfaces, and they claim that they give the lowest ice strength. And then there are hydrated surfaces. We will see all of them. And people have done experiments, simple experiments. As you can see, if you use a normal PDMS surface, super hydrophobic surface, super hydrophobic with infused oil, it may go down. So again, these are different approaches. And as I said, one of the most widely, used technique was to use super hydrophobic coatings. I mean, a super hydrophobic coating is the one where, water can, go down to a, tilted surface. This is advancing, this is receding contact angle. And, when you subtract receding from advancing, this is called contact angle hysteresis. And people said if you have low contact angle hysteresis, you will have a good super hydrophobic surface in order to get the super hydrophobicity, which is basically derived from lotus leaf surface. This is on the right hand side at the bottom, which is similar to this one. However, you can get rough surfaces. It has to be rough. It has to have micro and nano roughness. You can do it by different techniques, making a foam or etching a surface with an acid, depositing particles, etc. So you can get however, as you can see, I mean, application of these things, commercial application on any surface would be pretty difficult. However, this is the data. I mean, they combined a lot of data here. So where they plotted ice adhesion strength as a function of contact angle hysteresis. And as you can see, as the contact angle hysteresis goes down, I mean, ice adhesion strength also goes down. But here, look at this thing, the lowest, at least on this data, is around 100 kilopascals. But, we need to go down to 10. There are some new research where they have gone below 100, close to 10. I'm not going to discuss it. But, again, this was the main approach at the beginning. And these measurements were done at minus 10 degrees by using the technique I already mentioned. Now, I'll give you, some results from some of the people who are working on it. I mean, Ken Wynn is a good friend of mine. He's doing this research for many, many years. He was from Office of Naval Research, retired, came to Virginia Commonwealth University, and he mainly worked with, PDMS surfaces. So what he has shown, he used Silgard 184, this, common resin that you can buy. And he showed that when you cure it, I mean, there is an inverse relation between, thickness and ice adhesion strength. And as you can see, this is also around 100. Then he showed that, if you cure this resin at different temperatures, room temperature versus high temperatures, then the results change. So at higher temperatures, it's lower, but still very, very high. And then he said, what happens if we, texture the surface and add some oils? And as you can see now, by adding different types of oils, you can come down to almost like, 20 or so. So this is interesting. And Dean Webster, another good friend of mine who's at, North Dakota State University, he gave several talks at, Paint Istanbul in the past years. So it's a very large group. And, he uses silicone and PEO containing either glycerol carbamates or polyurethane, resins. So he basically prepares all these things. He's a good synthetic chemist and also surface chemist. He mixes them, he cures them, and then, he gets this coating, which has hydrophobic, hydrophilic, and, just the base polymer, neutral polymer. And then, so this is the chemical reaction. You can look at it. This is, epoxy terminated, so he cures it with amines. There's also urethanes, where he cures it with alcohols or, glycols or amines also. And they have done a lot of work. They prepared a series of polymers with different silicone content, silicone molecular weight, PEO content, PEO molecular weight. Look at the, contact angle, slip angle, surface energy, lots of things. So they really characterize them. They also looked at AFM images to find the surface morphology and how it affects the adhesion. And here, I mean, the lighter parts are silicone. So as you can see, as you increase the silicone, I mean, surface changes dramatically. And then they looked at the ice adhesion strength. And as you can see in some formulations, especially here, where they use, 10,000 molecular weight silicone and 750 molecular weight PEO, around 10% each, they obtained the lowest result, which was around 15 kilopascals. So this was pretty good. But depending on the composition, they gave, again, you can look at this paper, in this reference. Then he did the same thing with urethanes. He went through the whole thing because, again, he has a very large group. And here, here they use 1, 5, and 10,000 molecular weight PDMS. In the previous one, they used only 5 and 10. And here they have shown that really, when you have 10,000 PDMS with 750 PEG, I mean, you may go all the way down to, again, around, 15 or so. This F11 was the best one. And here F11 has, 10%, 5,000 PDMS and 10% PEG 750. So as you can see, I mean, and these are the last two are commercial formulations. So you see they can make better systems, better coatings than the commercial materials available. As you can see, these are around 20 or 25. Now, another one is the slip surfaces, slippery liquid infused porous surfaces. And here, I mean, this has been published and, quite a bit because, again, it comes from, Harvard. They even have a company which produces this. But here, first you make a, porous texture surface, solid, a polymer. For example, in this case, they use polypyrrole on aluminum and they use electrochemical coating, which is, quite complex. And then they filled it with a, either silicone type or fluoropolymer, fluoroliquid, just to make it hydrophobic. And then they said, this is slippery and icephobic, and, it really gives very good properties. Of course, if you can make it on this, huge wind turbine or, so basically, again, it's maybe a nice method, but it's very complicated, different to apply. And here, the best results, I just put the best result here, ice removal force they get at -10 is around, 16 kilopascals. And this is the paper, you can look at it. Now, they also looked at different surfaces. And then they compared microstructured, nanostructured, infused, and hydrated surfaces. Hydrated surfaces are interesting because they contain, water. Of course, if there's water, water will, melt the ice somehow. If you can keep the water liquid there, by adding, some antifreeze agents. However, after some time, this water or whatever liquid you are using will go away, will diffuse out and so forth. So again, it may not be that easy to keep these systems intact for a long, performance. So the best thing is, to be able to make a just simple thermoplastic polymer and coat it. Now, finally, there is a lot of work on the effect of crossing density and shear modulus. And here, this is a big group in Michigan where they have shown that either by using silicone or fluorinated polymers or polyurethanes, I mean, depending on the crossing density, which is the x-axis, the ice adhesion strength changes. So if the crossing density goes down, if you form, soft surfaces, then you will have low ice adhesion. So this is logarithmic. So it's not 1, but actually this is about 10, this is 100. So, and the same thing here. They say different mechanisms, slippage and non-slippage. So, with interfacial slippage, you can get, if you can design materials, you can get very good results. Now, finally, this is a work from University of Texas. They said, if we can form a surface, with two phases, one phase is soft, one phase is, hard and strong, so that it gives durability, and the other one gives, ice release. Then they use this formulation where, this sigma s is stress and the interface. So this is the stress of, or the force needed to remove the ice. And as you can see, this G is the shear modulus. So if you put a soft material with low shear modulus, then you can reduce this. That's what they, worked on. And they have some data. They show very, very low ice adhesion, and you can find this thing, in this paper. So I hope I was able to give you a, good overview of, icephobic coatings, at least some of the work done in the universities. And as conclusions, as ice and snow accumulation is serious problem, both in terms of safety and economic losses. And current methods of ice snow removal is difficult or costly. So basically you need a good coating that can, remove the ice without any interference. However, as far as I can see, that coating doesn't really exist. So we need lots of research, and it's going on. In fact, currently, we need to develop a high performance, highly durable icephobic coating that's easy to apply and repair. And of course, studies in both academic and industrial research laboratories are continuing, including our lab. Again, I didn't mention about, our approach. Hopefully next time when we have all of our results and we are, confirming those results by different, sources, I hope I can share those things with you. Thank you very much. And I'll be glad to answer any questions that you may have. Thank you.
Thank you very much, Professor İskender Yılgör, for this great presentation. It was indeed very informative on this very interesting topic. I am just checking for the questions we received. There is one question. Firstly, thanking you for your presentation, and then the first question is it known why and in what way ice doesn't adhere to the coating? And a second question from the same colleague is there a minimum force of ice adhesion that will substantially improve the impact of the icing problem?
The mechanism really depends on the environmental conditions. In one slide, I showed that the temperature, humidity, and if it's a wind turbine, the speed, so lots of things. And people are really trying to understand it. So, if the ice is coming, if it's snow, it will adhere differently. And then if it is rain and freezes immediately. So again, there's a lot of work. And that's really beyond my, expertise, because again, it's a totally different area of research. How ice really forms on the surface, adheres, and what are the driving. Of course, we need to understand all those things. And there are lots of different groups doing those type of research. And regarding, the minimum force, basically what happens, people have calculated that, if this wind turbine, again, we are more interested in wind turbine surfaces. Depending on their speed, at the lowest speed, if it is less than 10, the centripetal force will basically, throw the snow away. So that's why, we have this limit of about 10 kilopascals, which we are trying to achieve. And, people again calculated it by taking, into account the speed of these wind turbines, turning and the force generated and so forth, centripetal force.
I see here another connected question regarding the adhesion, measurement of the adhesion strength of the ice. So they, and the question is asking how this adhesion strength is measured. Do you use special designed equipment or simple pull-off or tensile tester?
No. You use a probe which can measure the force. So basically, you put the ice cube or whatever, and you push it with a probe. and that probe basically determines the force. So it's a very simple system. They can easily buy it, but they have to do it at low temperatures. Otherwise, it's not a stress strain type of work. It's just a probe. You push it and you try to break the ice from the surface, and then you measure the force.
I don't see any more questions coming from the audience, but I have one question. And I mean, also seeing the pictures, images from Dr. Scarborough's presentation during the keynote speech, the images from the plants in Texas. So
Yes.
we have seen how damage or how much economical loss it would give to producers, manufacturers. So seeing that, I really believe that there is a huge need for such a de-icing coating, and how I'm seeing all those literature or studies on this subject. How close do you foresee to have this technology available for manufacturers?
I mean, really, everybody is really working hard, and we are usually in contact with each other because most of the people working on these things are my good friends from Virginia Tech or Virginia. So basically, and we know how to synthesize polymers, how to control morphologies and things like that. So that's what we are trying to do. I mean, come up with a polymeric system that can really have, I don't know, low modulus, hydrophobicity, this and that, lots of things. And my main thing is that, it should be applied easily. So, I would prefer to have something like thermoplastic instead of thermosetting where you need to cure and all those things. But basically, again, we are approaching from the, different angles, but we are all people who can design polymers, although our main, interest is not, icephobic coatings, but since we can design and we understand the structure property and surface properties, I believe, because like Dean is very close to 10, we are very close to 10, in fact, below 10. Canvin is there, and, many other people, Tuteja and all those things. So I think there will be a simple coating available within a few years. That's my belief, commercially, which can go below 10.
Thank you very much. Thank you very much. Looking forward to hear your progress on this topic during the next Paint Istanbul. Thank you again for this great presentation and being